Yeah, first of all, thank you very much for the organizers for this amazing lecture. It's very nice. Yeah, I did my PhD in Stockholm, so I'm kind of local. And yeah, so two of my collaborators are in the audience. So there's Nordita, who is sitting over there, and Farhad, who is sitting over there. And otherwise, this is also, some work has been done with Laura Bernard, Cédric Dupayet, and Michael von Strauss, all in Paris. Okay, and I should apologize in advance because I'm going to speak about something that is kind of a technicality. Okay, so I cannot avoid becoming a bit technical, but I think it's an important technicality that everybody who works on massive gravity, this nonlinear DRGT massive gravity or bimetric theory should actually know about. So that's why I wanted to present it here. Okay. So first of all, a very short motivation, because I think Claudia has already motivated the question of why we should even consider massive gravity. But I wanted to give a slightly different approach to this, because even if we forget about cosmology and the problems of lambda CDM and so on, you can just, from very theoretical considerations, you can ask what are the field theories that you can write down. And we have the standard model, which is essentially a theory for particles of spin 0, spin 1/2, and spin 1. And they're all consistent, and we understand them very well, and so on. And yeah, so then you can ask, can we go to higher spin, right? And then there's spin 2, which is gravity, when it's massless. So we understand that, at least at the classical level, also quite well. And so if you want to go beyond this set of theories, then you essentially have two options. You can either just add more copies of the same type of theories, which is a bit boring, but yeah, sure, you can do that. Or you can add something new, okay? And in some sense, adding massive spin 2 fields is the minimal extension of the set of theories, okay? And I think it's therefore, alone for this reason, it's worth studying them. Good. And then, of course, you know about these problems with ghosts and so on, so we should find something consistent. And the only theory that is known, that's known to be consistent for a massive spin 2 particle interacting with a massless one, or with itself also, is this ghost-free bimetric theory that is based on the construction by Claudia and Gregory and Andrew, and was then extended to this bimetric theory by Farhad and Rachel. And I think most of you have seen this, but let me anyway explain what this action is. So the action is a theory for two spin 2 fields, or two rank 2 tensors, that interact with each other through a specific interaction potential. They are assumed to have standard Einstein-Hilbert kinetic terms. And in that case, where you assume this, the potential is fixed uniquely to this specific form. So in particular, there's a mass scale in front, and you have these 5 interaction parameters. Or it's really only 3, because beta 0 and beta 4 correspond to the cosmological constants. And then you have these functions, the elementary symmetric polynomials, the ENs that I have written down here. So they are functions of the matrix element. They take a specific form. This is not important for this talk, but just for completeness I put them here. But what is important for this talk is that they depend in a very specific way on the combination of the two metrics. And they depend on the combination with the square root taken off this combination of matrices. Okay? So there's this G inverse F, which is a matrix with one index up, one index down, and you have to take the square root of this matrix. And there is no other way to do this if you want to work with metrics, not with field lines. Okay? So you cannot avoid the square root. And yeah, so this square root has some problems. So two questions immediately arise. The first one is obvious. I think they're both obvious actually. So what we can ask is the square root matrix always well defined? So does it always allow for real solutions? Okay. And this question was essentially raised already in 2012 by Cédric and collaborators. And I will address this question. It has been addressed by different people, but yeah, I will give our approach here. And then the second question that I hopefully will get to in the very end, just very briefly, is there a simple way to treat it in computations, for example, if we want to do perturbation? Okay, but first let's go to the first question. So the definition of the square root matrix is, of course, I squared and I get the original matrix, right? And then the question is, what are the conditions under which real solutions for the square root matrix exist? And in order to get there, the first assumption that one can make is that we can do a simultaneous split, ADM split for both of the metrics. Okay? This is already a non-trivial assumption, but starting from here, you can then try to address this question. And of course, this decomposition has been used in the ghost proof also. Okay, so suppose we make the split and we insert it into this G inverse F and try to take the square root.
Why did you say it was a non-trivial assumption and make ADM split on both?
So as far as I understand, it is not obvious that you can actually make this split for both of them at the same time, because you have to have a common slicing basically of the space.
But I don't have to interpret it in terms of the slicing. I can just say this is how I'm parameterizing the components of the metric.
Okay. So you're just saying I redefine the metric components and call the functions like this?
Yeah.
No, you want to let them stand the
I mean, at least the
time
signature
variable
has
in
to
the
work
middle.
out correctly, right?
The signature does, yes.
You want
This is
the labs to
definitely-
stay in the front of the time variable, basically. So they need to have some kind of consistent
So you have to
consistent
stay on time for
Exactly, yeah. Which is essentially the, yeah. Okay. And, okay, so suppose that I insert that here and try to take the square root, okay? So then the idea is that we make a redefinition of ADM variables, and this is essentially the redefinition that has been used in the ghost proof also, to simplify this kind of computation. Okay? So if you, sorry, I should say what I'm doing here. So you see that the ADM variables in particular contain these shift vectors, right? So I call them capital N and capital L. This is important, right? And then there are the lapses, capital N, capital L without index, and the spatial matrices. I think most of you have seen this. Okay, but it's important that we know what this is. These are the shift vectors. Okay, so and we redefine these shift vectors now as follows. So it is the difference of the two shift vectors that gets redefined into a new vector, small n I. Okay? And the redefinition happens in this way. So this is kind of clear what it is. So just a scalar function multiplying the small n A. And here there is a three-dimensional square root d acting on this redefined shift vector. Okay? And I have not written down what this is because the expression is ugly and I didn't want to make the slide too messy. So, but there is just an expression for this three-dimensional square root matrix in terms of the ADM variables. It also contains the redefined shift vector. Okay? And the question is now, okay, so you have this and you insert it into the square root and you can take the square root. So you end up with something that has this D, this three-dimensional matrix inside, and something that has no more square roots. Okay? And also it has another square root of x in front, but this x is just a scalar. Okay? So there's one square root here that is problematic, or can be problematic, and there's this square root here in the D matrix that is now a three-dimensional square root. Okay? So we have reduced the square root by one dimension by making this redefinition. So the question reduces to, when do real solutions for this D matrix and the square root of x exist?
Excuse me, curiosity, do you see different branches of solutions? Because, for example, with real numbers, when you take a square root, you have plus and minus. With
Exactly.
matrices, you can have more.
Exactly. So this would basically just be, okay, in this, so I think in this case it would just be a plus minus here.
Only, you see only that plus and minus. No other. It's just
I'm
a
not
curiosity,
entirely sure. That's a very good question. Maybe forward, yeah.
So in this problem of reducing a 4-dimensional square root to a 3×3 square root, you don't see any value.
Oh, that's true.
Except
Yeah,
for the plus minus.
yeah, that's true. Because you have just removed this.
Assuming the ADM decomposition and doing it.
So there is no sense in removing the definition of D.
Exactly. But how many solutions you have for D, that could be a big question.
So this is the equation for D.
Look, I'm puzzled. This metric looks degenerate. This matrix is degenerate, right?
No, yeah, but there's more stuff here.
Ah, more stuff.
It's the problem sits in these two components. Yeah, that's true. I mean, this is not the full solution. No. But everything here is well defined and, you know, it's real and so on. So the problem sits in this part.
So there is already a plus minus in front of this term.
There should be a plus minus, yes.
Which means there are already two solutions.
Yes.
So how, suppose that everything works out, how do you choose the right one of these two? Suppose everything is fine, how do I know which one of the two square roots I should be using?
In some sense you have to specify. When you write down the action, you have to specify what you mean by your square root.
Okay, it won't be influenced because you can choose another individual parameters.
Yeah, okay, you can absorb it in the bigger parameters.
So it
Okay. Okay, and so now the idea to resolve this problem of the existence of the D matrix and the existence of the matrix of the scalar X is to further redefine in some sense. Okay. So in order to do this, we need to introduce Dreibein. So this is just the Vierbein, but only for the spatial part. Okay. So it's not connecting to a Minkowski space, but just to a flat. Yeah, I mean to a Euclidean signature. Okay. So we introduce these, and I should say that this is until here it has nothing to do with the Vierbein formulation of bimetric theory, because we're just decomposing the spatial metrics into these Vierbeins, and this is completely okay because we can always rotate these Vierbeins into the gauge where the two things are equivalent. Okay? Which is not necessarily true for the full theory. Okay, anyway, so, and this is also a specific gauge fixed Dreibein, which I'm not going to write down either because it's, again, too technical, but we have fixed the gauge here. And so by doing this, you can actually then write down a new redefinition. So now the new shift vector carries this spatial index, basically the spatial internal space index. And it's given in this way. So, and for this you see that you need these Dreibeins now for this definition. And essentially this corresponds to further redefining this previous redefined shift vector with this vector. And when you do that, so when you use this full redefinition, you can actually see that the D matrix always exists. Okay, so real solutions for the D matrix always exist. The D matrix does not impose any problems anymore. The only potential problems can come from the scalar x. Okay? So because the scalar x in principle could become negative, so that you cannot take a real square root. Okay. And the condition for us being able to take the square root and get a real solution is that this combination here has to be smaller than 1. Okay, basically the absolute value of this vector here has to be smaller than 1 of the redefined shift vector. And of course you can translate that into the original variables by just inverting this relation here and expressing it in terms of the original ADM variables. So this is a bound on the components of the matrix. Okay?
Is it like a usual bound on the shifts?
What do you mean, usual?
I mean, if you make the shifts too large, then you just invert the sign of the factor in front of the square.
I'm not sure if that's the same. So I will give you an interpretation of this bound on the next slide. Oh yeah, sorry. So, and this is, as I said, this is equivalent for the solution for x being big. Square root of x being big. Okay. So now I mentioned the Vierbein formulation already. So there is a relation of this, or in the interpretation of this bound in the Vierbein formulation. So the Vierbein formulation of bimetric theory has essentially been presented by Kurt and Rachel. And they decomposed the full metrics, so not just the spatial ones, but the full ones, into field lines. And wrote down a theory for these field lines. Okay, not starting from the metrics, but starting from the field lines. And in this case, there's no square root in the action, so you don't have this problem. But the resulting theory is equivalent to bimetric theory only if you impose the symmetrization condition. Okay, so you have to impose this condition if you want to make the two theories equivalent. And now, as it turns out, so you can argue that you want to achieve the symmetrization by Lorentz rotating one of the field lines. Okay? And then you can parameterize your Lorentz rotation by a boost vector, right? Or it's a rotation and a boost, and the rotation works out fine, and the problem really sits in the boost, basically. And in the end, it turns out that related to this boost, which is usually momentum, but you can translate it into a velocity. So the boost velocity vector that you need to define, so the velocity vector of the boost that symmetrizes the field lines from the usual ADM decomposition of the field lines is exactly given by this formula. Okay, so starting from an ADM decomposition of the field lines and trying to symmetrize them in this way by applying a Lorentz boost, you see that the Lorentz boost vector has to satisfy this equation. And this equation is exactly the redefinition that we saw earlier of the two shift vectors here, of the difference of the shift vectors. Okay? And since it is a Lorentz boost vector, it needs to satisfy this condition. Okay? Every Lorentz boost vector satisfies this condition. This is just the definition of the Lorentz equation. So, and this condition was exactly our condition for the square root of x being real. Okay? So this shows.
So this is the Desert value proposing the condition, right?
Exactly.
I mean, if you go beyond that, so the reason that you are not going beyond that is because you cannot prove that your theory goes free, right?
You mean the reason why you don't want to? So why
In
you
that
not
case,
why you not
because
just say that you're not imposing this?
Yeah.
Yes, I think then it's difficult to discuss the ghost issue. It's not clear.
So if I do that, it prove with the Firbein formulation directly that it goes free.
In particular cases, the equations of motion imply this condition. So this is in the beta 1 model, for example. Then the equations of motion imply this condition, and basically dynamically, you always sit on the bimetric branch.
I thought there was a later one. It was Bezer, I forget, but they did all the cases. To my knowledge, this is not the case, but.
So, I mean, if you go beyond that condition, then you are not finding the last necessary condition, right?
So if I go, no. So if I don't impose this, I don't impose this, so I don't impose the boundary. Yes, correct.
But to see the ghost freeness, you just need to reach this upper triangular gauge. You don't have to reach the desert gauge.
Yes,
And that one you can always reach, right?
No, that's the condition for reaching that gauge.
exactly.
Yeah.
No, it's
Yes,
the condition for reaching the upper triangular gauge.
yes.
No, wait. So what you're saying is that as soon as you're in the upper triangular gauge, the theory is ghost free.
Then the ghost freeness is more or less obvious. Yeah, you can see everything's linear, flat.
Yes. Yeah, no, that's true. Yes, but this is basically the reverse of what we're doing here. So if you want to go from the bimetric situation to the upper triangular,
From the Firbein to the upper triangle.
so from the general Firbein to the upper triangular.
Yeah. Then there's no obstruction.
And that, you're saying that would prove that the full Firbein theory is ghost free.
Yeah, at least for the primary constraints. Yeah.
So you can do whatever. You just need this to go to upper triangle. Or
Okay,
lower.
so Kurt is saying that you don't need this to go to upper triangular?
These are conditions to go from Einstein to simultaneously for two into lower triangle or up.
Exactly. So, okay, because I mean this of course works in reverse. So the condition for going from this to upper triangular by Lorentz transformation is exactly this.
But I want to start from the general unconstrained sphere line in the upper triangle.
However,
Is there any
So, in fact, Cedric had a paper in 3 dimensions where they showed that in general, starting from 3-dimensional Vierbein theory, you do not get the constraints.
that's
No,
true.
that doesn't mean you don't get them, they just couldn't see it.
Well, it was not obvious to them. Okay,
Obvious
I mean,
to
no,
them,
no, 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 but they wrote, they wrote the equations.
Yes.
Okay, the symmetrization condition did not follow from the equation that
Well,
they had.
only in exceptional cases. Only in exceptional cases. Only for some special parameter values. Generically, it follows. Generically, it always follows.
But the
But
symmetry,
you can choose some very special values, and then these are really exceptional cases.
the symmetrization condition is beside the point for seeing that it's got the right degrees of freedom. You don't need it. You can, as long as
Okay.
you can get
But
to
then,
this upper
then you
triangular.
have other problems.
Like what?
Okay, we can talk about it.
Yeah, maybe. Okay. So all I'm saying is this. So whether it's ghost free or not. Okay. So the ghost proof in the biometric formulation definitely is only valid in cases where we can take the square root, because otherwise the biometric formulation doesn't make any sense, right?
That's what I'm disagreeing.
No. Yeah. You disagree with that in the biometric formulation?
As long as if you start with the Vierbein formulation.
No, of course. No, that's what I'm saying. Okay.
Okay,
So then
fine.
all I'm saying is that go to the Vierbein formulation, you see that the obvious ghost proof, which is analogous to the biometric case, is exactly valid when this condition is satisfied.
Yeah.
Because this is when you can go to the biometric case. I'm not contradicting you now.
Sorry, no, I just
And in the remaining
confused by what you
cases.
meant by biometric formula. So the metric formulation of the biometric.
Sorry, exactly. Okay, yes. So in the metric formulation, the ghost proof definitely requires the existence of the square root. In the Vierbein formulation, this corresponds exactly to the case where you can get the symmetrization condition by a Lorentz transformation. So in this case, we can make the direct connection. Whenever you cannot do this, okay, we don't know the answer. Maybe you are right and the theory is ghost free. I don't know, but you know, I'm just saying that this is the connection between the two. Okay. Good. So first question is answered. So we cannot always obtain real solutions for the square root matrix. We need to satisfy this particular bound. Okay, and in this case, we can interpret this bound as a bound on this Lorentz velocity vector, which comes out naturally if you want to do it Lorentz course. Very good. So now I have one more slide about how to treat the square root matrix in perturbations. Because what you
One comment. But that bound then is actually satisfied by another equation of motion by weighting.
Okay, so if you start right, so if you assume the existence of the square root, what you're saying is that dynamically you don't run over the bound.
Yes, so the equations tell you that that bound must be satisfied.
Well, yeah, if you start from initial values that satisfy the bound. I mean, you need the square root to be well defined in the beginning, otherwise you cannot even derive the equations.
No, the equation that you derive for the Ni that tell you that bound is satisfied does not involve the weighting.
Sure, but I mean, in order to derive the Ni equations.
Yeah. So as soon as you reduce the 4D square root to 3D square root,
Yeah.
you see the bound before having to evaluate the 3D square root.
Sure.
And
Yes.
once the bound is satisfied, then you know that your 3D square root always exists.
Of course, this is the existence of the D matrix, which yeah, sure.
That's
Exactly.
it.
Yes. Okay. Very good. One last comment. So in very many calculations, you might want to vary the square root. Okay, just compute the linear variation of the square root around any background, say. And this is an ugly computation that has recently been done. But I mean, if you look at this paper, it's really a huge expression, and you might not want to work with it. Okay. So now there is a simpler way. So the idea is to work with variables which are not these fluctuations of the matrix directly, but you redefine the fluctuations into dynamically equivalent variables by basically just introducing the inverse of this variation into the variable. Okay? So you redefine the fluctuation of delta f, say, into some delta f prime, and of course you can do the same for delta g. And and include this inverse variation here, basically. And this inverse variation is actually very easy to compute. Yeah, I don't have time to show you this, but this is the outcome. So you basically work with a new variable. It's very difficult to invert this guy and compute delta f prime in terms of delta f, because this exactly involves the variation of the square root. Okay, so the inverse relation reads very complicated, but this relation is simple, and as soon as you have this variable, it is very easy to write down the variation of the square root in terms of this variable, because you exactly kill the complicated part, right? So, okay, the bottom line is I would advise you to work with this variable whenever you want to do one of the following things. So, for example, when you want to vary the square root in terms where it's not only coupled to itself, basically, okay? So for the interaction potential, this is not needed because you take the trace of the square root and then it becomes simpler. But for example, if you couple it to matter in some way, as has been done by Lavinia and Claudia and Haken, then you might want to use it. Or also for this calculation that has been done by Cedric and collaborators. So we're actually extending this calculation now and using the new variables. So there it's very useful. And maybe even, I don't know, the people who are experts in cosmological perturbation theory, maybe you will find this interesting because it might actually simplify many of your questions. Okay, so yeah, this is my summary and thank you very much.